Welcome back, everyone, to Session 2 of the CSAFE short course, Statistical Thinking for Forensic Practitioners, sponsored by NIST. Dr. Hal Stern from the University of California, Irvine, has returned to continue sharing his wealth of knowledge with us. Hal, go ahead and begin when you're ready.
Great. So thank you. It is exciting to be back. So here's an outline of the full three-part short course. 2 weeks ago, there was a discussion of probability and how it relates to forensic science. Today, we'll talk a little bit about statistics and some of the principles and how they apply. And then part 3 is an attempt next week to put it all together and shift the focus. The focus of parts 1 and 2 is on the probability of statistics with forensics as the examples, and the focus in part 3 is on the forensics with indication of how the statistics plays into it. So today we'll talk about collecting data, about variability, reliability, and accuracy, and then at the end about some of the statistical procedures that are used, estimation and testing and other. I will say, and I hope you find it to be true, the goal here is conceptual. A statistics course with the material we're talking about today would need to be at least 10 weeks. So 2 hours is less than 10 weeks, but I hope that and believe you can get some of the important concepts out. So in particular, the objectives I've set for our session today is to understand the concepts associated with collecting data and how probability and sampling can be used to draw conclusions about a population. And then, as I said, introduce statistical procedures. Before we dive in, we have a couple of Zoom questions to let everyone get to know each other. So here's some introductory questions. Where are you joining us from? What is your current profession or affiliation? And if you are a forensic practitioner, what areas are you interested in? So you should have a window should have popped up, and you can check one box for each question. It says multiple for each question, but hopefully you're only from one place at the moment. But you may have multiple areas of interest. So we'll give you a little time to fill that out. While you're doing that, I will repeat what Anthony said. You can put questions in the Q&A box, and I will try to navigate that and stop periodically and touch base on them, and hopefully have time at the end. And as Anthony said, I'm a professor of statistics at the University of California, and I'm coming to you from California, although I could be coming to you from anywhere because my office is completely surrounded by fog at the moment. Okay, Anthony, should we stop the poll? And as has been the case, as was the case 2 weeks ago, we have a mix of folks from across the United States and a couple from Europe, one from Europe, one from somewhere more exciting, and one from the future, who can tell me who to bet on in the football games this weekend. Okay, and then a large number of forensic practitioners, which is good because that's our target audience. And within that, a great deal of latent print and some of the other pattern disciplines, as well as a handful from trace evidence. The CSAFE, the center with which I'm affiliated, was funded by NIST with a focus on pattern evidence and digital evidence. I have found some levels of trace evidence, glass, for example, seized drugs, to be useful in talking about statistics. So some of those will come in as well. So thank you for doing that. There'll be a few other Zoom questions throughout. I hope you'll participate. It makes it much more enjoyable for everyone if we all share concepts. So with that all having been said, let's dive in a little bit. And here's the big picture that I introduced last week for those who were here last week. That's another question I should put in the Zoom chat. Were you here last time? So this is just a motivating picture, but for me, it's essential to kind of keep the big picture in mind. So we have some population that we're interested in learning about. Probability, which we discussed 2 weeks ago, it tells you how you can use knowledge about the population to predict what is likely to happen in the sample. And statistics is the reverse path. It is a set of techniques and methods that allow us to take information from a sample and try and draw conclusions about a population. So the first few slides and first few minutes are to talk about collecting data. Data are essential to the analysis of forensic evidence. When you talk to a statistician, they probably say data are essential to everything. And so for me, data comes up in 2 different ways. One is we will try where possible to quantify the evidence, that is characteristics of the evidence. These could be summaries of minutia in latent prints. It could be a chemical measurement from a sample or a measurement from a glass sample. But it's also some of the statistic ideas I would argue are relevant to developing and validating forensic procedures. So someone popped into the Q&A, I'd like to know the appropriate number of samples for doing validation studies. And I'll give you some idea about that towards the end of today's session. And so first step, where did data come from and how do we go about gathering data if we need data? And there are 2 fundamental ideas that I'll touch on. One of which is sampling, which is how do we actually choose a subset of the population to study. And the second is experimentation, which is what do we do on the sample that we've got? How do we carry out, for example, a black box study? A colleague of mine in CSAFE just finished a 2-session workshop on sampling. So I'm going to give you a few minutes, but it's possible to go into great depth on this topic. I try to motivate everything we do in this short course from forensics. And so here's a standard, ASTM standard about sampling seized drugs. And I wanted to just point out that if you look at this image, which comes from the standard, that some of the elements of my big picture appear in the box here. That is, there's a population, you come up with a plan, and then you come up with a sample. And the goal is to learn about the population by going through the sample. And so we want to say a little bit more about sampling. And here's again, from that same standard, I won't read it to you, you can read it yourself, but it goes into some detail about sampling and mentions there are different types of sampling strategies, both statistical or non-statistical. And we'll talk a little bit more about that right now. So I'm taking a very broad view of what we mean by collecting data and sampling. And so three examples are listed here. There are countless examples. You might want to collect a sample to learn about a population. That's a fairly standard use. Grab a sample of shoes and identify what's the frequency of size 10s or the frequency of size 10 Nikes or something like that. If you have a new instrument, you want to calibrate it or validate it. Taking measurements from that instrument would be collecting data. And we want to know, for example, as Bob asked, how many samples. And then experiments get to how do we collect data to decide if a certain type of training program is actually useful? Should I send all of my examiners to a short course to learn more statistics or to learn a new method of extracting latent prints? Is there value in that? A key message from a statistician is it's very important to think about how you collect data carefully. We take samples because typically the population we're interested in is really large, right? So if I want to learn about footwear, I could try to get data about all the shoes manufactured in the United States, for example, as a population, but it's an enormous number. And as was explained to me by shoe print examiners, it doesn't even count all of the counterfeit shoes and others that might be circulating in the US. And so sampling is a way to try and get information without going through the cost and trouble of getting an entire population. And as that standard mentioned, there are 2 major sampling paradigms. The standard used the term statistical sampling and non-statistical sampling. I tend to think about it a little bit differently. I think about what they call statistical sampling as probability sampling, using probability, laws and concepts and probability to draw a sample. And I think of what they call non-statistical samples as non-random samples. And we'll say a little bit about both of these concepts. Probability sampling is what statisticians try to encourage. The simplest way to think about this is the simplest sampling strategy, which is what's known as a simple random sample. And the idea of a simple random sample is if you have a population you're interested in, all University of California, Irvine undergraduates. I like to talk about a population like that because it's a real population. It's very concrete. There's about 37,000 such students. And we can think about that population and saying, I'd like to have 10 students to do a focus group and find out what they think about the return to in-person instruction. A simple random sample would mean every set of 10 students has the same chance of being chosen. So I would put the numbers from 1 to 37,000 in a hat, and I would draw out 10. That would be a simple random sample, and that's a probability sample. And the key point behind probability samples is, I'm going to argue and show a little bit, I won't show too much. If you use that approach, you can make fairly precise statements about how what you see in that sample informs you about the population. So if I took a sample of size 10 and I saw 5 males and 5 females, that would give me the idea that the UCI population of 37,000 people is roughly half male and half female. But of course, a sample of size 10 is not very large. And so there'd be considerable uncertainty. And in fact, I may only be able to know for sure, based on that the population is between 20 and 80% male. Right? But if I took a bigger sample, I learn more. And that's what we'll talk about as the session goes on today. I'm not going to go into detail about other probability sampling strategies. But as the middle bullet on this slide says, alternative strategies are to do more refined sampling. If I'm drawing a sample of size 10, I might be concerned that it's such a small sample, I'll end up with 10 males or 10 females, and that would be bad because it wouldn't be reflective. And so a stratified sample says, I can only afford to talk to 10 people, but what I'm going to do is I'm going to draw 5 males from the population of 5 females. So I split the population into subpopulations, and I randomly sample within each of those. And so any of these strategies are effective and can be used with the two statistical tools of today to tell me about the population. So what do we mean by non-random sampling? Well, it's not that we never do non-random sampling. We do it often. Sometimes it's not practical to do a probability sample. For me to draw my 37,000 students, a sample from my 37,000 UC Irvine students, I need to have a list of that population. If I don't, I can't identify them with numbers and I can't pick them out. If I want to sample the homeless in my city or town, I don't have a list. How do I sample them? So it's not that we never do non-random samples, but that they have limitations. The people that you sample may not be reflective of the population. One of the most famous examples of this is occurred in the 1948 presidential election of Truman versus Dewey. The political polling at the time was done with non-random sampling. Data collectors were sent out, for example, in the city of Chicago, and told to, your job today is to interview 15 people. 5 of them should be male, and 10 of them should be female, and 8 of them should be this, and 7 of them, right? And so the poll takers would basically walk the streets and try to identify people who met their assignment. Well, that's not a random way of sampling, right? And you can imagine that people look for, might oversample people in suits because they seem safe to approach. Relative to people who are, wearing sloppy clothing, just for an example. Or they may have a prejudice and take certain ethnic groups over other ethnic groups. And this, in fact, happened. The polling that was done in this ad hoc way indicated that Dewey was likely to beat Truman. And so that was the prediction made by the polling firm. And in fact, of course, Truman beat Dewey. So the dangers of non-probability sampling. More recent example, and many of you will know, a little bit more subtle, but when Trump ran for president in 2016 against Hillary Clinton, the polls were all predicting Clinton would win, and Trump won. What happened there? The challenge in doing a sample is it wasn't necessarily non-random sampling, but at the state level, it was very hard to do reliable sampling. And that's what led to those confusions. So some of the dangers in not using probability samples. So how does this all relate to forensic science? Well, consider that we seize a large shipment of baggage with white powder. If the question is only, are there any illegal drugs in the shipment, then non-random sampling may be sufficient. We might just say, let's try a few bags and see what we find out. If, however, the question was, what's the total weight of cocaine? You have to take a more systematic, statistical, probabilistic sample to identify what fraction of the bags have cocaine and how much do they weigh. Similar questions for other types of evidence we might want to get. So I mentioned sampling is one part of this of how we proceed. The second part of how we collect data is we might carry out a study. And so you can think about a black box study here as being what we're trying to think about. But I think of it more broadly than that. We might want to compare two training programs, right? I run a lab. I want my people to get up to speed on a new LIMS system we might have. And two different companies offer trainings. I might want to run an experiment to see which training gets people up to speed better, for example. So lots of types of experiments you can imagine. And just as in sampling, we had a distinction between probability sampling and non-random sampling. In experiments, we draw a distinction between observational studies and experimental studies, with the key distinction being in an experiment, we, the experimenters, control who gets what treatment. And so I will occasionally use a medical study as an example, because again, I think it's something we can all relate to, right? And so if I want to compare two different sorts of pain treatments, I could take people who are subject to migraine headaches, for example, and assign them to two different groups. This would be an experiment. When you get a headache, you'll use drug A. This other group, when you get a headache, you use drug B, and then you'll report how quickly your headache goes away. Right? That's an experiment. An observational study is when I just take a survey and I say, tell me if you use drug A and are you happy or not? Tell me if you use drug B and are you happy or not? And that's called an observational study. Randomized studies are considered, quote unquote, the gold standard. That is, they are the best way to try and determine whether there is a relationship between a cause and effect, or to determine whether drug A works better than drug B. And the reason is when you can take an experiment and randomly assign people to drug A or drug B, you can be assured that you'll get the same number of males and the same proportion of females, the same proportion of whites, the same proportion of blacks in each group, because you're doing it randomly. So a little digression. Why don't we always do random studies? Well, you can't, right? If we want to understand the impact of smoking, which was very, very important, 50 years ago, you can't carry out a randomized study and say, here, let's take 100 people in my study. This group of 50 is assigned to smoke cigarettes for 10 years. This other group is assigned not to smoke cigarettes for 10 years. And let's see who's healthier, right? That's not practical. And so instead, what people did was they said, let's find a group of smokers and a group of non-smokers, and let's study their health outcomes and see which are better. But those kinds of studies are very challenging. And I have an old and relatively simple, but I think interesting example. And this dates back to 1973. A study at the University of California, Berkeley looked at graduate admissions rates. So students apply for graduate school. 44% of the males were admitted, 35% of the females were admitted. There are large samples here, so this was quote unquote statistically significant. And it suggests discrimination, right? But when we look closer, here's the second bullet on this slide shows you program by program for 6 programs at Berkeley, the admission rates for males and females. So in program A, 62% of the males were admitted and 82% of the females were admitted. In program B, again, the females were admitted at a higher rate. Same in D and F. In C and E, males were admitted at a higher rate, but it doesn't seem like a particularly large gap. So what happened? How did we end up with an overall significant difference favoring males when program by program looks very similar, or if anything, seems to favor females? Well, there's another factor that wasn't taken account of in the simple observational study. We didn't look at the kinds of programs that males and females apply to. And it turns out that females applied disproportionately to programs that were hard to get into, and males applied disproportionately to programs that were easier to get into. And so we had 2 factors. They were applying to different kinds of programs, and the programs had different kinds of admissions rate. And so when you just total it all up, you get, I'm not sure what we call it, but maybe misleading inferences in the aggregate. And I will tell you something that I have found fascinating is this is known as Simpson's paradox, and it's covered in most introductory statistics classes. And you say, yeah, but how common is it? Well, we've all been living through it, believe it or not. There are a number of examples of Simpson's paradox that have come up in the COVID era. Here's one that's kind of, I can't go into great detail, but I found it a little mind-blowing myself. In England, they did a study of the degree to which the vaccine reduced hospitalizations. And they knew age was an important factor. So they looked at it by age, and they found that in people, I forget the cutoff, but I think it was in age 50 and below, the vaccine reduced hospitalizations by 87%. And in 50 and above, or above 50, the vaccine reduced hospitalizations by 93%. So a slight difference there. What would you guess? I should make this a Zoom question. What would you guess the combined effectiveness of the vaccine is when you just throw everybody into one pile? Turns out the overall effectiveness of vaccine in reducing hospitalizations is 75%. How's that possible? It works 87% in the under 50 crowd. It works 93% in the over 50 crowd. Yet when I combine them, it's 75%. It's another version of Simpson's paradox, which is the vaccine works well in both groups. More of the older group is vaccinated. That was true in England, it's true in the US. The older people are more vaccinated, but the older people are also more vulnerable to being hospitalized. And so when you pool the whole thing, it turns out that the vaccine appears less effective than it is because it's been disproportionately in the group that is at greater risk of hospitalization. And there were several examples like that during the COVID era. So the importance of thinking about all of the factors, not just relying on a simple data tally, shows you some of the challenge in doing statistical studies. So this is my little summary of what we've covered so far. The way we design a study has an impact on the results that we're going to get out. Sorry, this is not a summary. This is a last comment on how we do studies. And the key principles in doing a good study are the bullets in the middle of the page here. And I want to emphasize them and make a reference to the PCAST report. The key points are, when you do a study, it's important to try to compare 2 things, typically comparing a new drug to an old drug. I've discovered a new cancer treatment. I think it works better than the old one. I should do a study that compares the two, rather than just shift everyone based on my suspicion that the new one is better. I talked before about randomly assigning treatments to the units so that we assure the two groups are similar. We had a question earlier, how do I know how big a sample? I'm still not answering it, but that's a key question. And we want to make the environment as realistic as possible. And these experimental design principles are extremely important, and they're relevant to forensic science. I assume many people on the call are familiar with the PCAST report, somewhat controversial. But what the PCAST study did was it said, if you're going to do a study, you should follow these principles. And they were very similar to the ones I just laid out. And it was interesting to me, I'm not sure if everyone on the call is familiar with the DOJ response that was put out in January of this year. The DOJ response said, you know, the PCAST authors are wrong because you can do lots of different studies and you don't have to use all of these principles. And listen carefully because I'm about to say something I don't say very often. The DOJ response was correct on this point. That is, you don't have to do all of these things. But the key point that I hope you all know is PCAST was right. These are all good things to do if you can do them. The reason they're not always done is they're hard to do at times. But these are the kinds of things that make for more convincing evidence. One of the key points on this slide is PCAST and others recommend using blinding when possible. What does blinding mean? Blinding means when you're testing someone, say in a black box study, it's ideal if they don't know they're being tested, so that they'll use the exact same approach that they would use in a real case. So blinding is indisputably, to me, a good thing to do, but it's also understandably a challenge to do practically in a lab setting when you're buried in cases that you haven't been able to do, to use some of your time to do blind examinations of test cases. I can see why that would be challenging for a lab director. So you can see the tension between what we want to do, the best study principles, and what we can do in a particular setting. So here's a few times during the course of the session today, I'll have test yourself questions. So here's a test yourself question. This one doesn't have a Zoom answer sheet. The question is as follows. We're going to do a black box study of packing tape comparisons. So we get 50 volunteer forensic examiners who agree to participate in the study. Each is given 10 pairs of tape fragments, or a tape fragment and a roll, and asked to assess whether the questioned and the known came from the same roll. And so I ask a couple of questions here that try to pull together the concepts we've discussed thus far. One, what's a benefit of using volunteers in the study? And second question, what's a disadvantage of using volunteers in the study? And second question, some of the examiners don't complete all 10 assigned pairs. Is that a problem for us? Is the missing data a problem for us? So you can think about that a little bit. This is one of the types of questions that's a little challenging on Zoom, in the webinar format especially, since I can't call on people. I can't even let you talk to each other. So that's unfortunate. But give you a minute to think about it. And the slides that we sent out don't have the answer, but the next slide here does. So let's talk about this for a second. What's a benefit of using volunteers in the study? Well, in this case, it's an example where it's probably the only way to do the study, right? You can't make people participate in a study. And so that's the good thing about volunteers. They want to, they're willing to participate. But what's a disadvantage? Well, as we talked about, if you don't randomly pick a sample, how do you know the people in the study are representative of the population? They may be more experienced, they may be less experienced because, you know, they're willing to take a chance. So they may be older, they may be younger, they may differ in lots of ways. We just won't know that And so that's a challenge of using volunteers. Again, doesn't mean we shouldn't use volunteers, just means we should be aware of the challenge. And then I said, suppose the examiners don't complete all 10 assigned pairs. Are we worried about that? Well, we might be. Again, there's just not a great way to know the answer. It may be that people didn't answer the ones that they found challenging. And so if they got all the answers right, but only answered 60% of the examples, it doesn't mean they're always going to get them all right. On the other hand, it may just be people ran out of time and they wanted to move on and do something different. If we knew that was the case, we probably wouldn't care as much about the missing cases. Just saw a presentation about a black box study of blood print analysis. And the way that they did it to try and get away from this last issue is people couldn't go pick and choose cases. So they went in order. If they had to stop at some point, they stopped. But because of the design of the study, they could be sure that it was just a matter of time, that they didn't stop, that they didn't only do the easy examples. So that's the end of, if you will, a first piece of the course of today's session, which is the focus on data collection and study design. Very interesting topics. Again, they could be a course unto themselves. They are a CSAFE short course unto themselves. And so if you find that interesting or relevant for your work, I hope you'll pay attention and take the next offering we have of that type of material. Next set of topics I want to talk about, I've labeled loosely measurement, variability, and uncertainty. And I motivate these by a different standard, a standard for comparing trace elements. And so you can see this introduction from the standard, and the piece I put in bold shows you why we care about this type of measure, about taking measurements in a forensic context. We take some measurements, we compare the measurements in the questioned and known samples, and we try to see if things are indistinguishable or if they're matching, and try to use that to draw some forensic conclusions. To talk about measurements, I'm going to talk about different ways that statisticians collect data and how we think about measurements and the like. So lots of different types of data. Sometimes things come in categories like blood types or grades. Sometimes the categories are ordered, grades are, blood types aren't. And then most of what I talk about will be quantitative data. So where we have a numerical measurement, and this could be, for example, a refractive index of a glass fragment, which I tend to think of as a continuous measurement. You could get 1.5263, you could get 1.5264. If you wanted more decimal places, you could get more decimal places. And sometimes it's discrete. When we do firearms exams, we often look for consecutive matching stria, and that's just going to be 0, 1, 2, 3, 4, 5, 6, right? So that's called discrete quantitative data. And when we talk about measurement, it's really important to understand uncertainty. So much so that an ISO standard, one of the key ISO standards, mentions laboratories shall identify contributions to measurement uncertainty. And so whenever we measure anything, we acknowledge that there could be uncertainty. And the way that I think about this as a statistician is, if you measure something multiple times, you will not get exactly the same answer. Another anecdote, another presidential anecdote, some of you on the call, maybe many of you on the call, will remember the 2000 presidential election between George Bush and Al Gore, which was very close. And the state of Florida turned out to be essential. And they had some very unusual ballots. There were hanging chads and the like. And when they were doing the counting in Florida in different counties had different ballots. Every time they counted, they got different answers. And I happened to be at Iowa State University at the time. And I remember talking to colleagues, faculty colleagues, and And they were just didn't understand at all how that was possible, right? There's only one count. How can you get a different answer each time? And I found it interesting because it was an instance in which statisticians, which have kind of an unusual way about thinking about the world, are not surprised at all that when you count two sets of ballots, the same ballots twice, you get different count. And what I used to tell people was go take a ruler and go measure your desk in your office. Right? You almost certainly get different answers when you do it because you put the ruler down just a fraction off at the beginning. You may have it not exactly horizontal, lots of reasons. So this kind of, there is variability and it leads to uncertainty. Uncertainty and variability are two related concepts. But for me, uncertainty really reflects the notion that when you take a measurement, there's no knowing for sure what you're going to get. The ISO standard is really written primarily from the perspective of physical scientists who measure things like temperature, chemical concentrations. And so they're used to thinking about uncertainty as the measurement uncertainty. My thermometer is only accurate to within plus or minus 0.1 degree. Or this chemical assay is only accurate to plus or minus 5 parts per million. So there's a measurement uncertainty. Statisticians tend to use the term uncertainty more broadly than that. So they would include that, for example, but they would also include uncertainty because of other factors that have not been studied. So when the weather forecaster says the probability of rain tomorrow is 60%, they don't really mean a measurement uncertainty, but what they mean often is I have a statistical model and the statistical model depends on certain conditions. And when I run that model, I get different answers depending on what I assume about those conditions. And 60% of the time, the model indicates it's likely to rain in Orange County where I am today. And 40% it says it won't, right? So then I report that out to my audience as a form of uncertainty. So in the context of forensics and beyond forensics, it's important to understand that uncertainty manifests itself in several ways. And for me, this is when I begin to think about it as becoming variability. That is, when I think about, I'm not just going to take the one measurement, but I'm going to take multiple measurements. I think about different ways that might happen. I might take repeated measurements of the same object carried out by the same person. I might take repeated measurements of the same sample, a glass measurement, by different people. I might have measurements of different related objects. That is, if I take two fragments of glass from the same sheet of glass, what happens then? What happens if I have, so you have a lot of different ways that you can measure, and we might be interested in any or all of these. When we take multiple measurements, that to me is what I think of as variability. And we measure variability by looking at how the different measurements vary. And this slide lists a few measures. Some will come up later in the session. You may have heard of the idea of a standard deviation. A standard deviation says, when I take a bunch of measurements, there's typically an average. So if you take a test, there's an average on the test. Maybe the average in the class was 75. And then some professors, certainly statistics professors, will tell you the average on this test was 75 and the standard deviation was 10 points. And that means is that's kind of a typical deviation, the size of a typical deviation from the average. So some people got the average, 75. Some people might have gotten 85, which is, if you will, one standard deviation above the average. But there are other measures too. We might be interested in the range. What's the difference between the biggest and smallest value I saw, or other summaries of variability. So we have uncertainty. When I take a measurement, it may vary. We have variability. I've taken multiple measurements. How do I summarize that? And the third concept, reliability. And reliability is very, again, related. And reliability is key for us in thinking about forensic science. And so reliability to me refers to the consistency of a measurement or a measurement protocol. Will we get the same answer if we repeat the process? That sounds a little bit like variability, but here's one way that I think about the difference between them. We might have a scale that, for whatever reason, it's a little bit wacky, and so it's imprecise. When I put something on it, the answer that comes out could be off by as much as 10 pounds. It's hard to imagine a scale that bad, but suppose we have one. We're concerned about that. It's a little bit like using, an elephant scale to measure a suitcase or something. You're not quite sure how well it's going to work. So we have this scale that has large variability. That seems like a problem. But one way statisticians address problems like that is say, well, what you can do is measure the thing 10 times. Each single measurement is uncertain. Each single measurement has a lot of variability. But if you measure 10 times and take the average, you'll get a more reliable measurement. So a single reading may not be reliable, but an average may be reliable. And we'll shortly see why that could happen. So when we do reliability, I want to, for forensics, two key concepts come up. One is called repeatability. It asks whether you get the same measurement in two instances of doing exactly the same measurement. You can think about this in our black box studies that have been carried out in forensics. And I should probably stop here for a second and just say, I always do this, talking to forensic practitioners, assuming people know what I mean by a black box study. I've used the term a few times. I should probably define it, and I apologize for not having done so earlier. A black box study refers to a kind of forensic study that is happening now where you have an example, a questioned and a known sample of shoe prints, for example, where you know the answer. And you put it into an examiner. The examiner is treated as a black box. That's where the name comes from. We don't ask what the examiner is doing. We only ask what the examiner's answer is. So we have an input, a questioned and a known, where we know the answer, but the examiner doesn't. We give it to the examiner. We treat the examiner as a black box, and then we get the examiner's answer and see whether they got it correct or incorrect. That's called a black box study, and we do that lots of different times with lots of different examiners. In such a study, repeatability asks, what would happen if you gave the same example to the same examiner at a different point in time? You would hope that the same examiner looking at the same item would give the same conclusion the second time. That is a within-examiner comparison or an intra-examiner assessment. Reproducibility asks the question of, would different examiners give the same same answer to a given case? So repeatability and reproducibility are both interesting. They're both types of reliability, but they're slightly different. A third concept that we care the most about is not reliability, but accuracy. So lots of different terms here. Accuracy is the one that says, at the end of the day, did I get it right or did I get it wrong? Again, that works in black box studies because we know the answer. It doesn't necessarily work in an actual case where we may never know the correct answer. But in the black box study, you can know the right answer. And there's a really important couple the last two bullets on this slide are really important, one of which says, if I have a procedure that's very reliable, that is, every time you show me this, I give you the same answer. And not only that, but anytime you show it to one of my peers, they give you the same answer. That does not guarantee accuracy. So high reliability is a good thing. We're consistent as a field, but maybe we all stink and we all get the answer wrong, right? We hope not, but high reliability is necessary, right? If the field is going to be 100% accurate, we have to be reliable, right? If we don't give the same answers, we can't be 100% accurate. But being reliable itself is not enough because we could all agree and be wrong. So some subtlety to that. So when we think about reliability, I wanted to do an example. That's been me talking a lot. So the example I have is one that I worked on. I was working with some document examiners, and they were asking about, signature complexity, which a governing principle for examiners is the more complex a signature, the harder it is to simulate, and therefore the more definitive my conclusions might be. And so we collected data and we asked examiners to assess complexity. And one of the things I said to the examiners is, before we get too deep into this, we should find out how complexity judgments work. How reliable are examiners in making complexity judgments? And so here's what the data looked like. There were 5 forensic document examiners who agreed to participate in this part of the study. They were given 123 different signatures and asked to rate them on how difficult it would be to simulate on a 5-point scale. You can see some of the data here. The first simulated signature was rated a 4, a difficult to simulate by examiner 1, a 4 by examiner 2, but a 5 by examiner 3, a 3 by examiner 4, and a 4 by examiner 5. And you can see in this little table, which just shows you 5 of the signatures, that some signatures are easier to simulate than others, number 5, for example, but that different examiners have different thresholds for what they consider easy, medium, difficult, or very difficult. This is an example of a reliability study. We could talk about reproducibility. Did examiner 1 and 2 reproduce the same complexity judgment? And one way to measure that is the correlation. So I correlate the 2 columns of numbers. And what you find is the correlation is about 0.65. And that's considered good correlation, good reliability, not great reliability. You'd like 0.8 or 0.9 to be for a great, but so that was really interesting. The second thing that happened was, to me, even more interesting was we just took 5 of the examiners, and a month or 2 after they had done these analyses, we sent them back 7 signatures and asked them to assess their complexity. So this is a repeatability study, because this is now the same examiner looking at the same signature a second time. And they did that only for 7 signatures and only 5 examiners. So it was a small study. But when they did that, it turned out that the correlation was about 0.68. What does this mean? Well, one way to think about this, given how similar 0.65 and 0.68 are, is comparing me today to me next month is very similar to comparing me today to you today, right? That is, 2 different people are about as similar in their complexity judgments as the same person is at 2 different times. So that part was a little surprising and gave us a little pause. That's all I'm going to tell you about this part of the study. We're actually still working on it, but this was the first piece of it. So here's a little test question about reliability. This is a Zoom question. There are 4 question items here, and I'm going to ask you to say whether you think each one is true or false. So these will show up as 4 questions in a Zoom. You can move the little poll box, because one of the things I got in my course evaluations last time was a concern that the slide was hard to read and was blocking the Zoom quiz was blocking the slide. In this case, the Zoom slide is just reproducing the slide. The way that this is set up, because it's a little bit hard to do true false in Zoom, for each box, check the box if you think it's true. And so I'll give you a little bit of time to do that. And so this tries to reinforce some of the concepts we've been talking about in reliability, differences between repeatability and reproducibility, how they relate to accuracy and the like. When I ask questions like this, one of the things you can know is these are kind of some of the points that I think are important to know. please do fill out the question. Don't be shy. I won't know if you're getting it right or wrong. No one else will know if you're getting it right or wrong. Anthony, shall we reveal the answers? So 92% of people, thank you to the 48 people who responded, tisk for the 23 who did not. 92% said repeatability and reproducibility are both components of reliability. And well, let's see, I can go to the next slide. That is in fact true. Repeatability is a between examiner assessment is false. And again, the terms are confusing because repeatability and reproducibility actually sound pretty similar. And so this is just a nuance that we introduced to be able to make the distinction. Repeatability is accepted as meaning an exact repeat, so within the same examiner. And reproducibility is meant to be, can someone else reproduce? So that's the way the terminology works. Only 10% said high repeatability and high reproducibility guarantee high accuracy, which is good, and that is one of the important things I want you to know. And 63% said if a discipline is highly accurate, it will be highly reproducible. And of course, that actually is true. It is a little bit unclear because it depends on how accurate we're talking about. But to me, if I think about a discipline being 99% accurate, if we're talking about 99% accurate, if we're going to be 99% accurate, we all better be given the same answer. Let me address a couple of the things that have popped up in the Q&A. An anonymous person says, I guess, is that me talking in the middle of all the answer time? I just try to do that to entertain, but I can stop doing that. So thank you for pointing that out. And James mentions with respect to data collection, which I was talking about earlier today. If I want to do a study, a real study with lots of people, I have to go through an IRB, what's called an institutional review board. And they make sure that the study that's being done is valid and useful for science and is not taking advantage of people. And so IRBs are really critical to carrying out studies, but they definitely take time and can be challenging. And it's certainly in the realm of possibility that if I'm a lab director or if I have a good relationship and I go into a lab director might say, I'd like to do a small pilot study and you can use some of my team to do that pilot study. Generally speaking, when people are doing studies that might put them at risk, an IRB is essential. But when you're doing studies for, to learn how to do something better in the lab or like, you could probably get away without an IRB. So thank you for those questions and comments. That was great. So deep breath for me. We're going to segue from a discussion of measurement into statistics. So, and this is a piece that tells us how probability relates to statistics. So suppose we've collected data. I want to summarize the data. Just a couple of slides here to show you how I think about gathering and examining data. When we have data that's categories like blood types, we look at frequencies or proportions. And the data you see there are in fact US frequencies for different blood types, type A, B, AB, and O. They will come back in session 3 when we talk about likelihood ratios. Knowing frequencies or proportions like this is important. So that's why data collection is so important. The second example here is from consecutive matching stria. It's from a published study that was using an automatic algorithm to identify the number of consecutive matching stria in pairs that were non-matching. And so this was to generate, if you will, reference data that we could use to understand how large a CMS value could occur by chance. And so an automatic algorithm was applied to a large number of pairs of pairs of images. And this is the distribution. So again, we have the count and the frequency. In this case, notice that more than 90% of the cases had 0 or 1 matching stria. Whoops. For continuous data, and again, these are pictures that you'll see later and next week as well, we summarize it typically by showing some kind of graphical display and reporting numerical summaries. The data you see here are real data. They represent 49 fragments from a single source of glass, and on each fragment, a measurement of the refractive index was taken. And so here's a display of those values. They're all around 1.52, but they range from 1.5198 to 1.5201. And we have some standard summaries that we might give. So that's how we summarize data. But as we try to go from a data summary to a statistical analysis, a key concept is what's called a probability distribution. And so a probability distribution, to me as a statistician, is what are the possible values and how often does each occur? So you might go back here and say, oh, here are the possible values for CMS measurements in this population that was studied. 0, 1, 2, 3, 4, and 5 are the possible measurements. And here's how often they happen. 30% of the time I get a 0, 63% of the time I get a 1, 6% of the time I get a 2. Right? So that's what I would call a probability distribution. For the glass, the probability distribution is much more complicated because there's so many more values. I might have gotten a 1.51792. I might have gotten a 1.51793. So there's so many values, you can't really table them. And instead, we tend to describe them in some other way. And so that's what a probability distribution is. And I'm going to show you a picture with 4 examples of distributions. So these are the kinds of things that might happen. The binomial distribution, the top left, is the count of the number of successes in 10 trials. I'm a big sports fan. If I looked at 10 foul shots taken by each player, and the players make 75% of their foul shots, this distribution shows you that most of the time I'll see somebody make 8 out of 10 or 7 out of 10. I might see somebody make 9 out of 10 or 6 out of 10. But the binomial is a well-studied distribution. And so if I think it applies, it allows me to tell you exactly how unusual it is to see Shaq O'Neal make 5 foul shots when he normally makes 75%, for example, or something like that. The Poisson distribution next to it is an example of another variable for counts, but it works for how many accidents might happen at an intersection. And so we might expect 5 accidents. And so we would, again, not be surprised if we saw 3 accidents in a month at a particular corner, or 4 or 5 or 6. But we'd be very surprised for this distribution if we saw 12 or 13. And so distributions, again, tell you which values and how common they are. And there's 2 distributions on the bottom that I wanted to just mention. One we'll talk about. The normal distribution, or the bell-shaped distribution, is one that most people have heard about or seen. This distribution is one that's used in psychology. IQ scores are scored in a way that they have an average or a typical value of 100 and a standard deviation, a typical deviation of 15. And so this curve tells you that you expect to see 100. That's the most common value. But you wouldn't be surprised to see 95 or 90 or 85. Even 80 happens somewhat often, but 60 is pretty rare. The height of the curve tells you how often, but unlike the pictures on the top where there are bars that tell you exactly how often, the curve tells you roughly how often. And there are so many possible values that we don't list each value separately. The picture on the right is a different continuous distribution. It's called the log normal distribution. And you can see from the shape of it, it's primarily for values near zero, right? And so this could be, for example, when we measure chemical concentration of rare elements, we might generally see values near zero, but might get as much as 2 parts per million or 4 parts per million or something like that. We might use this distribution. The relevance of the distributions, I don't expect you to remember these 4 distributions or know much about them. The relevance is if I know how common it is to get an IQ score of 120, that may turn out to be useful information when I'm doing a study and I see 120. Or more to the point, suppose the number of matching minutiae, this is not a true example, but conceptually followed this Poisson distribution. Or sorry, CMS. The number of CMS followed this Poisson distribution. In a matching pair of images, I would expect to see 5 CMS of 5, but I might see 6, I might see 8, I might see 10, right? This tells me how common things are, and it helps me to assess the evidence. So that's why we think about these distributions. It's going to come back as we start to think about forensic evidence. But I'll stop there. That's a little intro to probability and how distributions work, which are key to the next part and the last half of the day today. Here's a repeat of my big picture. I told you at the start, statistics is concerned with how do I take a sample of measurements and draw conclusions about a population. The last bullet on this slide is new, and it says, here's how statistical inference could work for us. We might assume we know something about the population, collect the sample, look at the sample, see if it seems to support what I assumed about the population. And if it does, I might say, great, I understand the population. If it doesn't, it would require me to go back and think about the population differently and maybe make a different assumption about the population. That's purely a conceptual description, and what I hope to do now is show you how we might apply that. So I return you to the trace element standard that I started with 20 minutes ago or 30 minutes ago. This is about using laser ablation, inductively coupled plasma mass spectrometry. Some of you probably know what that means. I really don't, but I do know that it is a technique for getting chemical element measurements out of glass. And the standard says, if you use this technique, you can get high discrimination among sources of glass. You will be able to tell whether 2 sources of glass or 2 sets of glass fragments came from the same source or not. So that big picture that I just showed you applies here. It's a little more complicated. There are 2 populations. There's fragments of glass from the broken window at the crime scene. Those fragments come from a known source of glass. And then there are fragments that I may have recovered from a suspect's sweater that come from an unknown source. And I wonder if they're the same. The way that I think about the big picture is there are now 2 populations. Population 1, the crime scene sample. Population 2, the suspect sample. Or sorry, the population of glass on the suspect, population of glass at the crime scene. I have samples from each. I have a sample from the crime scene. I have a sample from the suspect. I wonder if the populations are different, and I wonder if I can use the samples to distinguish those populations. That, for me, is the motivation for the rest of what we're going to talk about today. And I won't walk through this in detail. There are a few people who mentioned being trace analysts. I don't know if there are any glass analysts on the call, but if there are, you may be familiar with this. This is literally from the standard, and it lays out a procedure for what to do. Take this many fragments, take this many measurements, compute the standard deviation. Remember, I described what a standard deviation was. If you don't have enough, if the standard deviation is too small, we're worried that it may be overly precise and misleading. So there's a rule 11.1.3 says, you know, if the standard deviation is below a certain minimum, don't use the standard deviation, use the minimum. right? And then it says, compute an interview and see if they overlap, blah, blah, blah. This is statistical inference. If you've ever read this standard or worked in this way, this is a statistical inference procedure. It is not the one that I would use in this setting, but it is an example of one. And we will show you what I might do, but it's very closely related to this. So this is my way of saying statistical inference, which sometimes when it's taught, including by me, is confusing and people wonder, what is this? Why do I need to know this? It just shows that it's a natural, it evolves naturally if you want to answer the kinds of questions that we're answering. Okay. So here's how statisticians think about the topic of statistical inference. The starting point is typically a parameter. So that's a new word in bold. A parameter is a summary of the population. So the key concept for comparing glass might be the mean level of aluminum in the glass fragment in the population. That would be a parameter I might be interested. And if I have two populations, I might want to know, is the mean aluminum concentration in the crime scene population the same as the mean aluminum concentration in the suspect population? If so, that would be incriminating, right? That would be evidence that they may be from the same source. Not that they are from the same source, but they may be. So statistical methods are basically concerned with learning about what I would call a population parameter. The way that we'll usually do that is we'll take a sample and we'll compute the mean of a sample. Notice these are different. The mean of a population, for example, could be the mean height of the 37,000 UCI students. That would be a pain to calculate, but I could conceptually and conceivably do it. It would take time to measure 37,000 people, but I could do it. I could take a sample of 20 people and just measure their heights. That would be a sample mean. These are different. The sample mean, if I have a good sample, should be close to the population mean, but it generally speaking won't be equal. And so as I mentioned in that big picture slide, what are we going to do? What we're going to do is we have a population we're interested in. We have a sample we collected. We're going to look at the sample mean. If we believe we have a good sample, we followed some of the principles we talked about earlier, then that good sample mean should be close to the population mean. And some of the probability concepts that we talked about 2 weeks ago, for those who were here, some of the probability concepts that I talked about 10 minutes ago, for all of us, as probability distributions, can tell us how close we would expect the sample mean to be to the population mean. So that's our approach. We want to learn about a population parameter. We're going to take a sample and use that. Statisticians talk about three different types of inferential statements. The first is known as a point estimate. Can the statistician give an estimate of this population parameter? What is my estimate for the mean height of UC Irvine undergraduates? I'll argue point estimates are not so great on their own. They're a useful starting point, but it's nice to not only give a point estimate, but also give some idea of our certainty. So that's called an interval estimate, where we say, my guess is the average height of a UCI undergraduate is about 5 feet 7 inches. But I'm very confident that the average is between 5 inches and 5 foot 9 inches. So I give you not just my best guess, but also some interval of plausible answers. And the last question is the one that says, I might want to test a specific hypothesis. Can I determine conclusively whether the average height in the UCI population is 5 foot 6? Or in our glass example, can I determine conclusively whether the two populations have the same mean aluminum concentration or not? So that's called a statistical test or a hypothesis test. So those are the three things I hope to run through in the next 30 to 40 minutes and allow some time for questions. Starting with the first, a point estimation is a way of taking a sample and getting an estimator of this population quantity. Suppose we want to estimate the mean of a population, right? On the bottom of the slide, I mentioned 3 ways we might do this. We might take a sample, a random sample from the population, record the average of the random sample, and use that as an estimate of the population mean. and you have my spoiler alert. That is a very good way to do it. An alternative would be to use the median. Take a random sample from whatever population you're interested in and use the median or middle value rather than the mean or average value. It is also good. It has some advantages over the mean and some disadvantages. The advantages, the median just looks at the middle value. And so if by some chance you measure, and make a measurement error and record someone's height as 12 feet tall, it's not possible. But if you compute the mean, it's going to get averaged in and may throw you off. The median just looks at the middle, won't have that. But assuming you don't have wild measurements, the mean is better than the median. The third example I have here is kind of goofy, but for me, it helps to refine the concept. Each estimator you can think about as a tool that I use to make estimates. The mean is a tool. Every time you show me a problem, I say, give me a sample, I'll compute the mean. The median is another tool. Here's another tool. It's kind of, we'll call it the stupid tool. It's like the stupid button. The stupid tool is, you give me a sample, no matter what the sample says, I estimate the population mean is 47. Here's the average height of UCI undergraduates. I ignore all the data and just say, good, I believe the mean height of UCI undergraduates is 47. Doesn't do very well in that example. You show me a set of test scores, I ignore the test scores and say, my estimate for the mean is 47. Well, maybe you get it right just by chance, right? So that's not a good estimator. Mean is a good estimator. 47 is not a good estimator because it's only right in very rare circumstances. So how do we decide what's a good estimator? Well, it turns out we tend to look for two things. One is called bias. This is the statistical use of the word bias, but it's very similar to the colloquial use of the word bias. We think of something as being biased when it's not accurate, right? It's an incorrect judgment, and that will apply here. And the second is variability. We might ask, how variable is an estimator? One of the nice things about 47, it's not very variable. It always gives the same answer. So here's a picture that I like to use. It's not particularly statistical. It looks like, from the shooting range, okay? So this is what I call a conceptual illustration. There's a Greek letter theta in the middle of these targets. That's because in statistics courses, theta is sometimes used to mean the population mean. And you have four pictures of what might happen if you shoot or if you take samples and estimate theta. The top left picture is really nice. I have an estimator here that has low bias. It tends to be around theta and low variance. Almost all of it is in the bullseye. The second picture, low bias. It's centered around theta, a little bit higher variance. Sometimes it's, a little bit further away from the truth, but still a good estimator. I'll go down to the bottom right. This is an interesting case. There's high bias. The answers are way off to the top right, and they're very spread out. They have high variance. We probably are not happy with this estimator. It does not give a reliable picture about theta. What about the bottom left? The bottom left is actually an interesting one for a statistician. Why? It's biased. It's not in the right place, but it's low variance, which means it's a pretty precise estimator. It just happens to be off kilter. And for something like that, you kind of wonder, if I could learn about the bias, I might be able to fix this one. So this is what I think of as talking about point estimates. I have a procedure that gives me one of these dots, and I think the dot, I want the dot to be close to the target, which is theta. The problem with the point estimate with one of those dots is it just gives you a guess, but it doesn't convey your certainty about it. And you'll remember at the start, I showed you an ISO standard that says, when we give measurements, when we report measurements, we should talk about their uncertainty. And I would argue that's true here too. When I make an estimate, I should be able to tell you how sure I am about it. And it turns out that we can. The standard error is the term that we use. to convey uncertainty. And so I'll tell you a little bit about what standard errors mean. And they're related to standard deviations, which we talked very briefly about earlier. And so here's a little bit that tells you. We start with the standard deviation. So I told you about my IQ score distribution. This shows you the distribution of IQs in the population. The mean is 100, the standard deviation is 15. They generally have a normal bell-shaped distribution, which is what you see here. And you don't know what I'm about to tell you is true, but it is true. And there are tables or computers can tell you this. It turns out 68% of the population has IQs between 85 and 115. A standard deviation 15, one standard deviation below or one standard deviation above. So that's the amount of the distribution that lies between 85 and 115, where my hand is jumping around a lot, is 68%. If you go out 2 standard deviations, you get 95%. So between 70 over here and 130 over here, 95% of that curve, of the area under the curve. So that's what a standard deviation tells you. A standard deviation tells you what a typical deviation is. And for a normal distribution like this, we can tell even more. Not only is a typical deviation 15, but 95% of the population should be plus or minus 2 standard deviations away from the mean. That is 100 plus or minus 30. That is between 70 and 130. So that's a standard deviation of a single measurement. When I use the term standard error, what I mean is, suppose I take an average. So this is a kind of a busy slide. The first bullet says, suppose I take 25 people from the population. Maybe I want to do a study of a certain population, left-handers to compare to right-handers. So I take 25 random left-handers, I give them IQ test, I get these values. The mean turns out to be 104.1, the standard deviation is 16.4. As you can see, because we know what I told you 2 minutes ago, that's pretty close to the right answers. But what happens if I take another sample of size 25? It says 5, but I mean 25. I get a different set of values, a different mean, a different standard deviation. This gets back to some of our earliest concepts from today. When you take a sample, there's uncertainty. A different sample gives you a different answer. There's variability. The mean, which should be 100 in the population, was 104 in the first sample, 96 in the second sample. So that's just the kind of variability we expect. And in fact, statisticians study this variability. They know about it. We can take steps even to reduce this variability. So let me show you a couple of pictures, and I appreciate the questions that are coming up. I will come to them. Let's go to that same normal IQ distribution and say, what happens if you take 25 responses? As I say, statisticians have studied this. There are mathematical results. I'm not emphasizing the math today. I'm just telling you what happens is if you take the average of 25 measurements, you end up with a standard error of 3. The standard deviation of one measurement is 15. The standard error of the average of 25 is 3. So if I take 25 and I measure them, this shows you what I would expect to happen. The mean should be 100. The standard error is 3. And as we said a few minutes ago, 95% of the time, I should get an answer plus or minus 2 standard errors. So if you take samples, the standard error is the information you want. It tells you how precise your answer is going to be. Your answer in this case is going to be plus or minus 6 from the truth. So here's a picture, and this gets to the very first question that was put in the Q&A box today. How do I figure out how many samples to take? Well, this doesn't answer for a validation study, but it says, suppose I'm measuring IQs, and I want to know the mean IQ. The first picture says, if you take samples of size 10, you'll get a mean of 100, and you'll get a standard deviation of about 5, a standard error about 5. So most of your samples will be between 90 and 110. If I take bigger samples, 25, then the mean will be about 100. Most of the samples, as I just told you, will be between 94 and 106. If I go up to 50 samples, even tighter. 95% of the samples will be between 96 and 104. If I go to 100 samples and take averages, again, even tighter. It's hard to tell. You get the answer would be around 100, and it would generally be plus or minus 3 away from that. And so this doesn't answer your question about how many, but it begins to tell you how you might think about it. These pictures could tell us how many samples we should take to get a certain degree of precision. And I'll come back say a little bit more about that, but this is the basic idea. Let me answer a couple of the questions that have come up. It says in the statistical inference target illustration, would we view bias as the accuracy of the alignment? I think that's an appropriate way to think about it. And variance as the shot-to-shot accuracy of the person operating the firearm. I think that's definitely a fair way to say that. We have some people who are steadier and would have lower variance, and some people who are unsteady, a little bit more movement, and they might have high variance. And the bias is their average. So it talks about how accurate their sighting is. It's a little subtle because, right, this part of the variance is their sighting is moving more. Could be their sighting is moving more, or it could just be they always sight in the same place and then they twitch a little more. But I think those are definitely helpful ways of thinking about that. So thank you for that. Carl asked about players being in the zone, but a little off topic. So time permitting at the end, maybe. If not, I'll invite you to email me and I'll give you the answer. I have studied the hot hand and it is an interesting topic, but not too forensical. So here's what we might do to build on the ideas I just shared. We call that an interval estimate or a confidence interval. And a confidence interval is an interval based on our sample data that will contain the right answer with a specified degree of confidence. And what I just walked you through informally was the idea that you can get a 95% confidence interval for this parameter that you're interested in by taking a good point estimate, the mean, plus or minus 2 standard errors. And that's what I was doing in this previous slide. I was talking you through that by saying, if I take a sample of size 100 in the bottom right, the mean should come out to be about 100, but more importantly, the standard deviation is around 1.5, or the standard error. And if you go plus or minus 2 standard errors, you go plus or minus 3. And so that would be the precision or the confidence interval for a measurement with 100 samples from a population like this. I should clarify one thing. You'll notice I've been flipping back and forth between standard deviation and standard error. Standard deviation, to me, always generally means one measurement. Standard error means the average, how precise is the average of a number of measurements. But, and please ignore this if it confuses you, a standard error is just a standard deviation applied to the average of a certain number of measurements. I apologize if that's confusing, but I thought it was important to say to make sure I get it right. The plus or minus 2 standard errors is known as the margin of error. So if you've ever seen a political poll reported on the news, they'll typically say 55% of people prefer candidate A, but the margin of error is 5%. And so that means 55% of the people prefer candidate A, but the truth in the population may be anywhere from 50 to 60%, the plus or minus 5. And here's how it works in a forensic setting, right? I might be interested in the mean aluminum concentration for a crime scene sample, and I have 10 glass fragments. I compute the mean, compute the standard deviation. It's 10 measurements. This is how you get the standard error. Again, more details than you probably want to know or need to know. but the standard error turns out to be 0.013 in this case. And my 95% confidence interval says my best guess is this, the concentration of aluminum is 0.73. But the confidence interval says I wouldn't be surprised if the true mean is between 0.704 and 0.756. This kind of interval was used in that ASTM standard that I showed you earlier. They were telling you to build a confidence interval. They were building more than a 95% confidence interval. They were building a 99% confidence interval because they wanted to be more precise. An important point here, again, a confusing point, but an important point. How the confidence interval get interpreted is this. 95% of the intervals that you build using the statistical recipe that I'm describing will contain the right answer. Very similar to what we find when people testify in court. Knowing that the procedure works 95% of the time does not mean that it worked in this particular instance. So there's the distinction between how the procedure works in general and did it work in a particular instance. But we believe if we have good procedures that work most of the time, that it'll work in our case. Marissa asked, what's an acceptable error rate? Here, I wouldn't use error rate. I would use margin of error. And the margin of error, the margin of error that you might want depends on what you're going to do, right? How precisely do I need to know my accuracy? Knowing that this test is 95% accurate plus or minus 2% might be good enough for you. Knowing that it's 95% accurate based on a small sample plus or minus 10% would not be very helpful, right? So the margin of error is the thing that we control. Bob asked, how do we know how many samples to take? Marissa asked, what's an acceptable error rate? In this setting, statistical approaches like this confidence interval and the math behind them tell you how changing the sample size will change the margin of error. And so those two questions come together. If I need to know what percent of the bags in this suitcase of white powder contain drugs, I might take a sample of 100 bags from the suitcase, little baggies, and test them and determine that 70% of them seem to have cocaine. And I want to use that information to, I'll weigh the bags and I'll be able to tell if this rises to the level of a felony or not, right? Whatever. I'm making stuff up. I don't know the law, right? But I might take a sample. My point is the statistical part, not the law part, is I might take a sample of 100 bags and find 70% of them. Well, it turns out, again, this is just me telling you, you have to believe me, with a sample of size 100, the margin of error, right, is plus or minus 10%. So taking those 100 bags and finding 80% had cocaine only tells me that the truth is liable to be between 60 and 80. You say, how many samples do I need? Well, is knowing it's between 60 and 80 good enough for you? Then that's enough samples. If that's not good enough, you feel like your district court requires that you know things plus or minus 5%. It turns out you need to sample 400 of the little plastic baggies to get plus or minus 5%. And so that's how we do this. That's the trade-off that's involved. Okay, so let me go on. And this is some of the points related to this question that Bob and Marissa are both hinting at. How precise do I want things to be? Well, what determines that is how much confidence do you want? Do you want 99% confidence? Do you want 95% confidence? How precise are the individual measurements you're making? If they're not very precise, then you're going to need more measurements to get a narrow margin of error. How many measurements? We've talked a lot about that. So these are the types of considerations that go into figuring out how big a sample to take. Last topic, and we can leave Marissa and Bob's questions up because it comes up here too. Last topic in inference is probably the most important because the language is very common in the world and it's very confusing as well. Suppose I want to test a hypothesis about a population parameter. The way that we're going to talk about this is always imagining we have two samples. It applies in one sample, it applies in three samples. Suppose I have two populations I'm interested in. The most common scenario is medical testing. I take people who have high blood pressure, I'm worried about them. I have a drug A, it lowers blood pressure. And I have a new drug B that I've discovered, and I think it's better than drug A at lowering blood pressure. And so what am I going to do? I think about this as having two populations. I have a population of people with high blood pressure who I give drug A, and I have a population of people who have high blood pressure I give drug B. And I want to learn the mean decrease in blood pressure in those two populations. You can imagine why that's important to test. The way a test works is there's a null hypothesis. The null hypothesis is the hypothesis of no difference or no change. I have a new drug B. I think it works better. I want to test whether it works better. I test it by starting with the opposite. I start by assuming it doesn't work better. There's no difference. So that's the null hypothesis. And we almost always want the alternative hypothesis to be true in this case. We want the new drug to be better. So the application in medicine is just like that. It happens over and over. Two drugs to compare, take a sample, compare the samples, try to decide if you can draw a conclusion about the populations. Start by assuming the null hypothesis is true, there is no difference, and see if you can disprove that. The way that we do this is a statistical test leads to something called a p-value. You may have heard of that. One of probably the most confusing concepts in all of statistics. Don't be frightened, we can do this. The p-value measures the strength of the statistical evidence against the null hypothesis. As I said, we start by assuming the null hypothesis is true. We do a test, we get a p-value. If the p-value is small, we will often say, oh, the evidence is strong against, so low p-value, strong evidence, we call it a statistically significant result. This is a very controversial area, and I will go through it in a little bit more detail. There are two types of errors when carrying out a test. A type 1 error would be the null hypothesis is true. The new drug works the same as the old drug, but you said it was better, and maybe it's more expensive, and that would be a very bad decision. We call that a false positive. A type 2 error is when the null hypothesis is false. The new drug is better, but you didn't realize it. So that's a false negative. Right? You said no difference, but when in fact there was a difference. We usually are much more concerned about type 1. That is, we don't want to change everybody's drug if in fact the new drug is just the same as the old drug. But there's a trade-off here. If I try to avoid type 1 errors at all costs, I might never reject the null hypothesis, and that means I'm going to miss out on the good drugs. And so the terms type 1 and type 2 error live in this world. I'm comparing two means, there's a null hypothesis. We've sometimes taken type 1 and type 2 errors into forensics, I believe incorrectly, because the language of a false positive is kind of loaded. And so for those who were here 2 weeks ago, I emphasized this point then too. In forensics, we really think about false identifications and false exclusions. In testing, we have a single conclusion about a null hypothesis. It is either correct or incorrect. And that's why we end up with false positives and false negatives. And in this context, we call them type 1 or type 2. I try not to use type 1 and type 2 except when I'm doing a test of this type. I saw a question pop up about the previous topic, so I'm going to put a pin in it and come back to it later. So the basic idea of hypothesis testing, again, you're not in 2 hours going to learn statistics and how to do it all. This is the concept. We have a hypothesis that the difference between the two populations is 0. And the way that we test it is we come up with a point estimate for the difference. And we ask, is the point estimate close to this hypothesis? And the standard error helps us make that judgment. And the notion is, I have these two means in the two population means. I think they are the same. I get two sample means. They're close to each other, but they're not exactly the same. And I ask the question, if they really were the same, could I see a difference like this? And that is what the p-value asks. The p-value says, what is the chance that I would get two samples that are this different if the null hypothesis is true? If they're really the same, could I take two samples and see a difference? That's what the p-value is trying to measure. Very confusing in my view, because it's asking a hypothetical. Suppose the two populations are the same. I get two samples. They appear different from each other. There are two reasons they could differ. They could differ just by chance, or they could differ because, in fact, the populations are different. The p-value is trying to compare those two, but it can only answer one question. The p-value can only say, could this have happened by chance? That turns out to be really important for us. So here's how it plays out in the setting that we're interested in. There's a crime scene, glass fragments at the crime scene. There's a suspect, glass fragments on the suspect. We think of those as two populations. And now we have these two samples from those populations. So I have the Greek letter mu with the word scene, which says that's the mean aluminum concentration for the population of glass fragments at the crime scene. And then I have the Greek letter mu suspect to be the mean aluminum concentration for fragments from the population of suspect glass on the suspect. Those are the two population parameters of interest. I want to do a test. I want to test whether suspect's mean matches crime scene mean. You can see that this is exactly analogous to my medical test. So I can use the tools of statistics to do this. Suppose I have 10 glass fragments from the scene, the control sample, typically call that Y, 9 from the suspect, call it X, get the mean from each, expect that to be near 0. We get a difference. It's not exactly 0. We use a computer and a procedure known as the t-test to get the p-value. And the p-value gives us an assessment of whether this could have happened by chance. And here's how we're going to use that p-value. Here are two examples. Ignore the picture on the right. Let's focus on the left. The left basically should look familiar to you by now. It's a bell-shaped curve. In this case, the bell-shaped curve is looking at the difference in the means. And in the first case, I'm saying, suppose I got a 1.3. 1.3 could happen, right? The height of the curve it's not the top of the curve, but it's kind of in the middle. Could happen by chance. The p-value says, suppose the mean is 0, which this curve has. How likely is it that I would get a 1.3 difference in my two samples by chance? And the hatched lines here are that probability. That is the p-value. In the picture on the left, it says, you would expect to get a value of 1.3 or bigger about 19% of the time. So that could have happened by chance. The picture on the right says, suppose I repeat the test, different glasses, different case, and this time I get 2.3. That's much more unusual. The chances of getting test statistics out here, 2.3, 2.4, 2.5, or negative 2.5, right, depending on which was bigger, is much smaller. It's only a 2% chance. And so James asked a great question. That 5% cutoff that I was using, is that equivalent to reasonable doubt? It may or may not be. As I said, people often use 5% as a cutoff. What are they doing? They're basically looking at these two pictures and they're saying, in the picture on the left, the difference that I saw could have happened by chance 19% of the time. Therefore, it does not convince me. I'm willing to believe it was just a chance deviation. The picture on the right says the difference I've seen here would only happen by chance 2% of the time. And I may decide that is so unusual that I don't believe it was chance. So it's not equivalent to the use of the term reasonable doubt in the courtroom necessarily, but it is analogous. That is, it is each individual might have a different threshold, right? I might decide 2% for me is so unusual that I think something's happening here. It did not happen by chance. You might have a different threshold. You might decide, you know, for me, it has to be below 0.01 to convince me that there's something happening here. And one of the things I don't like about these tests is that you have to you don't have to, but people pick a cutoff. The p-value is really a continuous measure of evidence. The lower the p-value, the stronger the evidence that there's a difference. The higher the p-value, the stronger, the less evidence that there's a difference, right? More consistent with being the same. So let me cut through the last few slides and save some time for some questions. This is what it might look like in a specific case, right? So these are just plugging in some numbers of two sets of glass fragments. The mean in one sample was 5.3. The mean in the other was 5.9. Again, I won't bore you with the details, both because they're boring and because we don't have a ton of time. And in this case, the 5.3 and the 5.9 yield a p-value of 0.15. Again, the statement is, if these two populations really had the same concentration, you'd want X bar, you'd want 5.3 and 5.9 to have come out the same. They didn't, but the difference I've seen, 0.6, could occur 15% of the time by chance. And it is common in science to say, well, 15% could really just be a chance agreement. Important to note that what it means is there's not evidence here to reject the null hypothesis. It is not safe to conclude, aha, these glasses definitely came from the same source. It's much more tentative than that. It's much more tentative than that. It says, I can't be sure they're different, right? I don't think they're different, but I can't be sure they're the same either. Sorry. Okay. A few more comments before, and then the questions. Statistical tests do seem to relate to key concepts in the justice system. That is, we can say null hypothesis innocent, alternative guilty. That's one way to interpret what it means to say that someone is innocent until proven guilty. The null hypothesis is innocent. We start with the null and we only reject it when we see enough evidence. One of the reasons that I said I don't like to use type 1 and type 2 in this world is a type 1 error in the statistical sense would therefore mean deciding that someone is guilty when the person is innocent. But I don't think any of us would call this a false positive. That is, it's not a positive outcome, right? So our main point here is only to try and show you where the analogy works and where it doesn't. We should not use type 1 and type 2 in forensics. I'm going to close here with a few points about testing. A key point, this is my opinion. I always try to distinguish between fact and opinion. This is strongly held opinion. Statistical hypothesis tests, I don't think, are a good match to analyzing forensic evidence. Why? There's a logical problem. The statistical test assumes the null hypothesis is true. It assumes the glass samples match until proven otherwise. But matching glass fragments are incriminating. So we don't want to assume they match until otherwise. We want to assume they don't match. And so when we say two samples are indistinguishable, as that ASTM standard does, it says we can't distinguish the means. It does not mean they are the same. And the standard doesn't say they're the same. It just says, I can't distinguish them. But I always worry that that sounds a lot like they're the same. And so that's a danger. And we will talk much more about that for those who come back next week. I hope you all do, when I talk about how forensic analyses work and some of these dangers. last few slides, I'm not going to talk through in great detail. They're basically relate test and confidence intervals. And I encourage you to read these if you're interested. Tests are very popular, but I would argue more popular than they should be given some of the limitations. So here's how I summarize hypothesis testing. It does not treat the two hypotheses symmetrically. The null hypothesis is given priority. This is appropriate if there's a reason to believe it, which I believe is the case in medicine. I don't believe that to be true in forensics. P-values are used as the ruler for measuring the evidence, but they depend a lot on sample size. That same 5.3 and 5.9 that I got, and I said, gee, that's not a significant difference because it's based on 10 fragments. If I saw 5.3 and 5.9 and they were based on 100 fragments, it would be significant. So that power of the evidence depends on how many measurements I take. That's also a little bit troubling. And the interpretation is, for me, by far the most important. It cuts two ways. Rejecting the null hypothesis means that you've seen a difference that you don't believe could have occurred by chance, but it does not necessarily mean the difference is important. It just means it didn't occur by chance. And the second version, which I've already emphasized, when you don't reject an hypothesis, it doesn't make it true. And so there's a notion in statistics of a power of a test. Is this test well designed? Will it reject if it should? And we don't spend enough time talking about that. I have a test yourself question. Here I have two of them. I'll tell you what, you can read this. I'll be quiet. I'm going to read your questions. And then we'll put up a zoom on this. So this says I'm measuring mean weight of bags of drugs, if you will, and I want to get an estimate of the mean weight. And so I do my confidence interval procedure, and then I ask you about how different things might affect the confidence interval. Go ahead, Anthony, you can put that up. Okay. Okay, let's show answers for those who were brave enough to dive in here. Anthony, there you go. So let's see how we did. If you took a bigger sample, as we've said, the confidence interval gets narrower. Good. If you wanted more confidence, it would get wider, but we were less sure of that. I'm not sure who Gertrude Cox is either. I'm not sure why that showed up here. It seems like it was carried over from a previous quiz. Last question was a trick question, really interesting. When you do statistical analysis, there's a very interesting finding, which is the size of the population turns out not to matter very much at all. It's primarily the size of the sample that matters. And so if there were 100,000 bags and I took the sample size 100, that would be almost identical to if there were 1,000 bags and I took 100. So that one was a trick question. Okay, thank you for that. Second question is about p-values. And so I'll let you look at that for a minute. So in this case, I've done a test and gotten a p-value of 0.23, and I want to see how you can interpret this. You want to put up the quiz? and I will give you some time to think about that. I will tell you only one thing about this that you can ignore. It's a little background noise. It is, I asked this question of all statistics students, including PhD students in their thesis defense. So this one is not an easy question. There are multiple items here. You can pick more than one. Okay, Anthony, let's show the answers.
They're flying in right now. I think people are finalizing. So
Okay.
While they do that, I'll tell you who Gertrude Cox is.
Okay, I know.
An American statistician born in Dayton, Iowa, whose academic advisor was George Snedeker, after whom the statistics building at Iowa State University is named.
Thank you for that. Yes,
That was my trivia for the day.
very well done. Okay, which of these statements are true? P-value of 0.23, and here's the last slide. So we had 18% agreeing with the first one, 48 the second, and 35 the third. As I say, this is confusing. I think it's the kind of thing that takes multiple hearings to get right. One of the nice things about having the video available. 0.23 says, I saw a difference in aluminum concentration. It could have happened by chance 23% of the time. And so the first says we would be likely to reject. And the answer for me is I would probably not reject. I would say, oh, this happened by chance. Interesting sidebar. The night before the Clinton-Trump election, Nate Silver had a 25% chance for Trump to win. And it was, everyone said, oh my God, the polls were wrong. Nate Silver was wrong. If you don't know who Nate Silver is, I apologize. But in fact, 25% chance things happen by chance. That's, flipping a coin and getting heads twice in a row happens all the time. And so in this case, I would say not true. The high p-value means they could have occurred by chance. So don't reject a null hypothesis. That for me is true. That's what I would have said. These samples can't be distinguished based on these data. That is basically true. The more precise statement is the population means can't be distinguished based on this data. And the samples came from the same window is not true. We can't be sure of this no matter what. And that was good. I don't think anybody said that it was. So this is what I believe we achieved today. And I have 5 minutes to answer a few questions. So I will do that. Statistical procedures are used sample data to draw conclusions about a population. We saw a few different approaches. I emphasized at the last half hour hypothesis test. And what these do is next week, what we'll see is how these tests are closely related to some very common approaches in forensics. And we'll also talk about likelihood ratios and why some people, including me, like them because they address some of the concerns here. So now let me address some of the questions in the Q&A box. They're really excellent questions. James asked, comment on a difference between a p-value of 1.99 and 2.01. I have 2 comments actually, James. First is p-values can only be between 0 and 1. So you can't get a p-value of 2.01. But your question is excellent. What's the difference between a p-value of 0.06 and 0.04? I would say that's a very small difference. And one of the things that disturbs me about the way testing is taught by statisticians and done in the real world is someone would get a 0.04 and say, oh, my professor told me 0.05 is the cutoff. So 0.04 is an important difference. 0.06 just misses the cutoff. It is not an important difference. That can't be right. They're measures of evidence. 0.04 and 0.06 are very similar evidence. And so think about the p-value as a measure of evidence. The lower it is, the stronger there is evidence of a difference. Heather asked a great question. Why isn't the assumption that the known and unknown means don't match? And Jeff Salyard, who's listening on this call and who I've been exchanging emails with for a while and who works with us at CSAFE, he's been telling me this for weeks. You're exactly right, Heather. It is the natural way to frame the question is to say, I have two glass samples. My null hypothesis, my starting point is they don't match. And let me see if I can reject that and find some conclusive proof that they do. The reason we don't do that is the standard statistical paradigm, which I showed you, needs a more precise hypothesis. The hypothesis that they don't match is not precise. They could not match and be off by 0.01. They could be off by 0.02. They could be off by 0.10. They could be off by 672. And it's just a technical thing. It's hard to build. If your hypothesis was they differ by 672, I could test that. But if you just say, is there any difference? There's not a good statistical way to test it. There is a way that I don't have the time nor inclination to do now. Again, it's a tease to come back next week. I will tell you next week how you might change the procedure to do this, to do what you say. But it's an outstanding question. Thank you. And I think the one other question is from M. Eggert. If there's a threshold for sentencing enhancement based on the total weight of a drug, would it be more informative to determine the probability that the measurement is above the threshold than to determine the margin of error? This is a really good question as well. And it's going to be one that I'm going to struggle to answer in 2 minutes, but I can actually run over a minute or two. My next meeting will wait for me. There are both ways that I might think about addressing this. And it is tricky for the same reason that the previous two answers were tricky, right? Let's just suppose, and there's a case I read about once where, a suspect was caught with a bag like this, and some of the bags contained drugs, some didn't, and then there was some variation in the size of the bags. And so they wanted to get the total weight. And so they did a statistical analysis to get using the margin of error approach. And they came up with, based on our analysis, they built a confidence interval for the total weight. And they said, my estimate based on a statistical procedure is the total cocaine weight is, I'll just make up some numbers, is 30 grams plus or minus 10. So that's one way to proceed, but suppose the threshold is 25 grams for it becoming a sentencing enhancement, for there being a sentencing enhancement. Knowing that it's your best estimate is 30, which would suggest this longer sentence. The uncertainty, plus or minus 10, suggests wait, it could be 20, so maybe I shouldn't give the enhancement. So you can see why the confidence interval might not satisfy a court. They might be concerned about that. And so another way would be to do what you suggest in the question, to try and say, based on this analysis, my probability that the weight is above 25 grams is whatever, but it turns out, and this is related again to some things that will come up next week, giving a probability like that is actually kind of hard to calculate because it requires knowing a little bit more than we typically know. So it is a challenge in these settings for how we do it. Most often people just rely on the point estimate. Here's my best estimate, it's 30 grams, let's do the sentencing enhancement. As a statistician, I always think the margin of error is important and might say, if I was a judge, go back and take more precise measurements or more measurements, sample more bags, so you can get the confidence interval down as we have discussed. Your questions are very reassuring to me because they're good questions and they indicate that even if we're not getting everything, we're getting the issues out on the table. So I'm gonna, it's 10:01, not too bad. Thank you all for your attention. Encourage you all to come back for the exciting conclusion in week 3, where we take probability from week 1, statistics from week 2, and try to marry them together and directly address the 3 common ways that forensic evidence is analyzed: as expert opinion, as what I call a 2-stage procedure, and using likelihood ratios. So thank you for being here.
Hal, thank you so much for continuing to guide us on this journey. Everyone else, thank you for joining us. and we hope you have a great day.